Okay, so I changed the title of my topic a little bit. It's now embedded sensors for CMC engine components. Recently, I've done work with strain gauges as well as thermocouples, so I thought I'd include it. I would include it. Sorry about that. So let's start. So what we have is a CMC material. It is silicon carbide fibers encased in a silicon carbide matrix. They're both polycrystalline. And so what you get out of this is a material with very excellent thermomechanical properties, and it's even better than super nickel alloys. So in future jet engines, in the hot section, this CMC material will be preferred over the super nickel alloys. But the issue is that the material is a ceramic. CMC stands for ceramic matrix composite. And so the issue is we can't use conventional instrumentation, that is to say, wire thermocouple and wire strain gauges, as we would with super nickel alloys. So we need clever ways of detecting the same conditions. So in this case, in this presentation, it's temperature and strain. The sensors that we employ on these devices or on these surfaces have to fulfill some kind of criteria. They need to be able to survive high temperatures. Around 1000 is typical in the hot section of a gas turbine engine. They need to have low mass so that they don't affect the vibrational mode of the components. And they also need to have low profile so that you don't affect the gases flowing through the jet engine. So I'm going to start off with temperature sensors, thermocouples. So most of the work that we've done in the past was with thin film thermocouples, platinum palladium as an example. So at high temperatures, we had a lot of issues with these, such as dewetting of the thin films, diffusion, small diffusional distances, and selective oxidation of the palladium films. So as you guys know, thermocouples are just made of two conductors which are connected at a point. And so we thought that we could potentially use this silicon carbide CMC material as part of the thermocouple. And the little picture below shows one of the thermocouples that we actually made. And so we thought that if we could incorporate this material as part of the thermocouple, we could bypass all of these issues that affect thin film thermocouples. Another reason why we leaned towards using this bulk material was that in literature, people had combined platinum with silicon carbide, monolithic silicon carbide, and achieved thermoelectric powers of 188 microvolts per degree K, which is large. So we wanted to kind of replicate that. But with this approach, there were some issues. The material itself from the picture before, you could see it has a very rough surface, so that makes it hard to employ thin films on it. And the dielectrics that we use, shown here, this is molite. It's very hard to pick an appropriate dielectric because of thermal expansion coefficient mismatches between the dielectric and the CMC material. So you have to use the correct dielectric. So this is the setup that we use for testing. We have an aluminum chill block shown here. We feed water or ethylene glycol through in order to keep it at as low of temperature as possible. On it, we have our sensor. One end of it is cooled on the chill block, the other end is heated. And so we put the free floating end in a tube furnace, and that thermal gradient from hot to cold is actually the driving force that produces the thermoelectric potential. We have two type K thermocouples measuring the hot temperature and the cold temperature, and the sensor itself has platinum wires which extend out to a DAC system, and we get voltage readouts from the sensor. So this is just a schematic of how to make one of these and just a rough view of what they look like. So we start off with a bare CMC substrate, coat it with a dielectric, heat treat the dielectric, and then the third step, which is the most important, we make a hole in the dielectric where we want the platinum to make contact with the CMC material, because the CMC is one conductive part of the thermocouple and the platinum will be the other. And where they meet is where the voltage will be produced. So this area here is where the voltage is produced, and it's roughly in this region here. So we went ahead and tested this idea, and this test was done for two reasons. We want to know the maximum thermoelectric output of these devices, and we also want to evaluate its stability over a 5-hour hold period. So in this test, we can see that 250 microvolts per degree K is increased or is produced, which is higher than what we saw in literature, but for reasons that I can explain if someone is interested. And in this region here, we see that the voltage drifts at a rate that's proportional to around 2.6 degrees Celsius per hour, which is relatively low for a semiconductor thermocouple. So then we went ahead and tried to test at even higher temperatures. And the mentality here is we're trying to go now 100-degree increments. So our goal temperature is 1000 degrees Celsius. So here we start at 500 and the sensor works. We go to 600, the sensor is fine. And then we try to go up to 700 and the sensor fails at around 660. So the reason why it's failing here is that oxygen is now diffusing through the platinum and reacting with the silicon carbide, forming a layer of silicon oxide which lives between the platinum and the silicon carbide. So we had to figure out a way to prevent the oxygen from diffusing, and so we came up with this approach. The processing steps are all the same, except that now we sputter coat a layer of indium tin oxynitride, and it has a great ability at preventing oxygen from diffusing through it. And so we went ahead and tested that, and we had a pretty successful test. 500, 600, and 700 all worked well. So our next step was to see if this approach could survive even higher temperatures. So it survived 700, and then we try to go to 800, and it fails. So now the mechanism that's happening here is that there's no oxygen in this region, but now the platinum is reacting with the silicon carbide. So we had to figure out a way to prevent that from happening. And so a coating worked the first time, so why wouldn't it work the second time? And so that's what we did. We sputter coated a pre-coat of indium tin oxide. It's non-stoichiometric and it's very conductive. And the reason why we chose it is that we want to maintain an ohmic contact at this region. So we went ahead and tested this. And this test starts at 800, which is already a 100-degree improvement over the previous thermocouple. And then we go to 900, it works again. And then as soon as we try to go to 1000, the sensor fails. And 1000 is actually our target temperature. It's a typical temperature within the hot section of a jet engine. So this is as far as we've gotten with thermocouples. We need to make a 100-degree improvement, but we're almost there. We'll be there within a month or two. So now I'm going to shift gears to strain gauges. In their most basic form, a strain gauge is essentially a resistor. And so my knuckles here would be the resistive material, and then the two metal leads, which you can connect to a breadboard. So that was my thought when I designed this strain gauge. So we have here two platinum leads, which connect directly to the CMC material. Both of these little circular regions make contact with the CMC material. And so the interesting aspect of this approach is that the CMC material can actually sense its own change in resistance. So this is the setup that we use. This is a custom-built 4-point test rig. Each of the little cylinders here are equally spaced apart, so that when we apply a load on this surface, it's uniformly distributed. The sensor itself has a student strain gauge mounted so that we can measure the strain that we apply, and we force a current through, and with platinum wires extending out to a data acquisition system, we can actually measure the voltage drop across and relate that to Ohm's law to measure resistance. So this is a typical test done with one of these CMC strain gauges. And as you can see, every time we apply a load, every few seconds, the strain gauge here in blue responds with a change in resistance of about 4 ohms. And this translates to a gauge factor of around 20, which is pretty high when you compare it to metal gauges, but pretty average when you compare it to semiconductor gauges. So just to conclude, we were able to make these sensors successfully. The thermocouples performed well at about 900 degrees Celsius, but we need to get them to 1000. They were also able to produce thermoelectric voltages of around 250, which is pretty high. The higher it is, the higher the resolution of your reading. Same with the strain gauges. We got gauge factors of around 20. But for future work, we need to improve the performance of the thermocouples by 100 degrees to get it to 1000. And the big thing about the strain gauges is that all the testing that was done was at room temperature. So we actually need to test this at higher temperature because this is going to be advertised as a high temperature strain solution for the CMC material. But the only issue is that we have our strain rig, it's too big to fit in a furnace. So we know the equipment we need, it's just a matter of funding. Finally, I would like to thank the NASA Glenn Research Center for providing the substrates that I used, the HPI Incorporation for the dielectrics that I used in the study, and also the URI Research Foundation for funding me last year when I did this work and supporting this work. That's it from me, but I'll be happy to take any questions.